Hello everyone, welcome to our presentation on the optical full adder project. This work was developed by Guo Zijing, Fang Yuze, and Liu Yujun under the guidance of our instructor, Professor Zheng Yujie. We designed and simulated a full adder circuit using only optical logic gates, and we're excited to show you how it works. Let's begin with the project goal. Our objective was to build a full adder circuit entirely out of optical components. We achieved this by simulating digital logic functions with light, using interference and waveguides instead of electronic transistors. The advantage of this approach are low power consumption, high speed operation, and the potential for miniaturization, which is essential for future optical computing. This project explores what logic computation could look like when powered by light instead of electricity. This slide presents the overall logic structures of the full adder. You can see the truth table showing the relationship between inputs A, B, and Cin, and the outputs sum and Cout. In our implementation, we used combinations of optical XOR, AND, and OR gates to build this logic. Each of these gates were simulated using different waveguide arrangements and optical components. Here, we show the complete layout of the full adder circuit as designed in our simulation environment. Every part of the circuit, from signal generators to combiners and waveguides, is based on optical principles. We'll go through each gate one by one to explain how we achieved logic behavior with light. First, XOR. To achieve the XOR behavior, we use phase space interference. The phase difference is defined by the formula. Delta phi equals 2n plus 1 multiplied by pi equals 2 pi and delta L divided by lambda. By setting m equals 1 and n equals 1, we get delta phi equals 3 pi, which leads to delta L equals lambda times 1.5. This means the longer waveguide should be 1.5 times the reference wavelength, ensuring destructive interference happens only when the inputs are the same, which is the key requirement for the XOR behavior. Here's the logic behavior table for XOR. As expected, the output is 1 when the inputs are different, and 0 when they are the same. On the bottom left, the spectrum display simply shows the wavelength of the optical signals that help us confirm we're working on the correct optical frequency. On the right, the time domain signal plot shows binary output levels over time, confirming the XOR logic response. Second, OR. Unlike the XOR gate, the OR gate doesn't rely on phase difference or interference, so there's no need for any phase turning here. Any input that is 1 contributes optical power, so the combined signal is non-zero as long as at least one of them inputs is high. The truth table shows logic behavior of the OR gate. If either input A or input B is 1, the output is 1. The only time it outputs 0 is when both inputs are 0. Looking at the bottom plots, the signal on the left shows the raw combined output, while the signal on the right shows the filtered result after digital processing, thanks to the expression block. Last, AND. The logic behavior here depends on phase control interference. The key formula is also as the same as XOR. But what's different is that the CW laser is used to multiply the waveguide length and help reverse the phase when needed. This controls whether interference is constructive or destructive. Only when both inputs are 1 do the signals align constructively. That results in a high output, which is what defines an AND gate behavior. The truth table summarizes the AND gate operation. The output is 1 only when both input A and input B are 1. At the bottom, we see the results from the simulation. But most importantly, the plots at the bottom demonstrates wave reversal. The first plot shows that the input wave, and the following plot illustrate how the CW laser and the waveguide caused phase inversion, which is a critical aspect of how the AND gate was achieved. The third plot shows the output after the optical expression operator filters the result, clearly making AND logic behavior. Thank you for watching our presentation on the optical full adder. Through this project, we've shown how optical gates, XOR, OR, and AND can be built using waveguides, lasers, and interference principles. We believe this simulation lays the groundwork for a future where logic computation can be faster, more efficient, and completely powered by light.